flight of the U.S. Navy's A-7 was in September 1965. The present Navy configuration, the A-7E, appeared in late 1968. By the end of our participation in the Vietnam War, Navy A-7s had flown 40,000 sorties and dropped over 90,000 tons of bomb.
A large number of enemy targets have had the accuracy of the A-7E weapon delivery system demonstrated. The enemy knows that irrespective of weather, day or night, or defenses, the A-7E will pinpoint those targets.
First flight of the U.S. Air Force version, the A-7D, was in early 1968. These aircraft entered combat during the final months of the Vietnam War. They flew 12,700 sorties and delivered over 20,000 tons of ordnance.
A-7D aircraft are equal to or better than the 10-mil accuracy predicted. Forward air controllers are impressed with its weapon delivery accuracy, the ability to kill targets on the first pass. They are quoting numbers of bombs dropped within 10 meters of the target.
The A-7 is a single-place light attack fighter, 46 feet long and 16 feet high. It has a wingspan of approximately 36.5 feet, or 23.5 feet folded. Normal landing weight, assuming ordnance expended, is about 23,000 pounds. Minimum landing roll is about 3,000 feet. Maximum field landing weight is over 37,000 pounds. Low maintenance requirements and fast turnaround capability are designed into the A-7. 90% of all pre-flight service and maintenance is accomplished without special work stands or aircraft jacks. Non-structural skin between the mid and lower longerons allows for quick opening maintenance panels and doors. Self-test features are built into the major avionics and systems to eliminate a need for complex ground equipment on the flight line. Internal fuel capacity is 1,500 U.S. gallons in the A-7E and 1,425 gallons in the A-7D, carried in several fuselage tanks and an integral wing tank. Up to 1,200 additional U.S. gallons can be carried in 4 external fuel tanks on the inboard and outboard wing stations. Automatic ejector pumps are used for fuel transfer. All ordnance is carried on 8 external stations. The 4 outboard wing stations are stressed for 3,500 pounds each. The 2 inboard can carry 2,500 pounds each. 2 500-pound fuselage stations are designed to carry defensive missiles. The A-7 carries 1,000 rounds of 20-millimeter ammunition and an M61 Gatling-type gun with pilot selectable fire rates of 4,000 and 6,000 rounds per minute. With varying combinations of racks and adapters, the A-7 can carry every ordnance item in the NATO arsenal. Primary electrical power comes from an engine-driven constant-speed drive AC generator. A transformer rectifier produces DC power for specialized circuits. The Air Force A-7D has a nickel-cadmium battery for self-starting and emergency power. A retractable ram air turbine provides emergency electrical and hydraulic power. Emergency extension of landing gear, flaps, and ram air turbine, and control of wheel brakes is provided by a nitrogen-charged hydraulic accumulator. A-7 control surfaces are driven by dual tandem hydraulic actuators through mechanical linkage. Outboard ailerons and inboard spoiler deflectors provide excellent lateral control, with roll rates up to 200 degrees per second. The empennage consists of a unit horizontal tail and a conventional rudder. High lift surfaces consist of full-span leading edge flaps and slotted variable position trailing edge flaps. An automatic flight and trim control system augments the pilot's inputs to provide a consistent response, regardless of load. The primary flight control system is optimized for the attack mission with emphasis on high-speed, low-altitude maneuvers. The airframe is designed for a 4,000-hour fatigue life. However, service experience indicates this number to be conservative. The positive load factor is 7 Gs at about 30,000 pounds combat weight. Air Force and Navy pilots who flew combat in Southeast Asia are familiar with the mission effectiveness of the A-7. The Air Force mission payload was generally 8 Mark 82 bombs, 2 Sidewinders, 1,000 rounds of 20mm ammunition, and full internal fuel, plus 2 300 US gallon external fuel tanks. With this payload, the Air Force had a 480 nautical mile radius of action. When operating from Korat, all of Southeast Asia fell within that radius of action. The Air Force could loiter 20 minutes at altitude and be in combat 10 minutes and still have about 1/2 hour fuel reserve at landing. A Navy mission lasted about 2 hours. Ordnance load was 10 Mark 82 bombs, 2 defensive missiles, and 2 offensive missiles. No external fuel tanks were used. Even without external tanks, the Navy pilot had about 1 hour reserve fuel upon return to the carrier. Before takeoff, the inertial platform gyros are aligned by setting the inertial measurement set for a north, east, and vertical coordinate reference. A fast align technique is available, as well as an airborne align capability, using Doppler inputs as a reference. Before takeoff, navigation and target data can be entered into the computer. Position coordinates of navigation checkpoints or targets are simply typed in. Up to 9 locations may be entered. These can be selected or changed in flight. While en route to or from the target, should the pilot see another possible target, he can record its location using the computer position mark function. The position coordinates are recorded at the press of a single button on flyover. Up to 9 locations can be entered and recalled later for future attack or intelligence purposes. Before takeoff, the pilot selects the location of the first navigation checkpoint on the computer. The A-7 engine is an Allison TF-41 of the 15,000-pound thrust class. Maximum takeoff weight is 42,000 pounds, allowing a fuel ordnance payload of 20,000 pounds. Takeoff roll on a standard sea-level day with this maximum load is approximately 5,000 feet. Considerable design effort has been devoted to creating a comfortable environment for the pilot. While minor differences exist in the location and appearance of some cockpit features between the A-7D and the A-7E, functions are nearly identical. The cockpit is comfortably wide. Low consoles provide easy access to all controls. The pilot's field of view over the nose and sides is excellent. Many displays and controls are located on prime cockpit surfaces for ready visibility. They are arranged functionally for proper accessibility. Most are symbolic for easy recognition. Generally, navigation and flight instruments are centered on the forward panel. Pilot oxygen is provided by a 10-liter converter. 10 minutes of emergency supply is contained in a parachute seat bottle. The seat ejection system is designed to operate at speeds from 0 to 650 knots. And at altitudes from ground level up. Service experience has demonstrated the system to have a very high success rate. A successful combat mission requires navigation to and from the target and delivery of ordnance precisely on target. The extreme accuracy of A-7 navigation and weapon delivery is based on an integrated system of 8 major avionic components. They are the central computer, the head-up display, the forward-looking radar, the inertial measurement set, the Doppler radar set, the armament station control unit, the air data computer, and the projected map display. For simplicity, the 8 major avionics components may be classified as either sensors, controls, or displays. These components all interface with the computer, which acts as the brains of the system. The computer receives a continuous stream of data from sensors and controls. It processes the data and outputs information to pilot displays. In addition, it performs navigation and weapon delivery computations and acts as a control to integrate all system functions. It also monitors the reliability of data inputs and performs self-test functions. Sensors provide flight data and target our navigation position data. The inertial measurement set is the basic sensor for the measurement of aircraft handling, attitude, and velocity in 3 axes. These data are supplied to the computer for both navigation and weapon delivery computations and to appropriate pilot displays. The Doppler radar continuously measures and displays ground speed and drift angle. This information is available as a reference velocity for air alignment of the inertial measurement set and as backup navigation information. The forward-looking radar provides data for 2 primary functions: weapons delivery and navigation. In weapons delivery, it provides air-to-ground slant ranging and range and azimuth cursors for radar bombing. A TV display is also provided for use with certain optically guided weapons. In navigation, it provides high and low altitude ground mapping, low altitude terrain following, and terrain avoidance. The air data computer uses total and static pressures and total temperature inputs to develop true airspeed, corrected indicated airspeed, Mach number, and altitude. Controls enable the pilot to communicate with the system. He enters and extracts data from the computer, selects operating and attack modes, aims the attack systems either visually or with the radar, and commits the system to automatic weapons release. Location of the pilot's controls on instrument panels and consoles has been optimized to reduce workload. The armament station controls unit is pre-flight programmed. It inputs to the computer the selected weapons type and releases stores from selected stations on computer command. It also establishes station release priorities and the proper sequence of release. The system communicates to the pilot through displays. They show navigation and weapon delivery guidance, flight information, advisory data, and cues. The projected map display uses 35mm film strips of standard aeronautical charts as a moving background for the aircraft's present geographical position and ground track. It can also be used to update navigation, radar correlation, or enter the location of desired geographical features into computer memory. Map coverage is of the entire area or theater of operations. The head-up display projects various symbols into the pilot's forward field of view, allowing him to receive continuous data and cues while keeping his eyes out of the cockpit. The flight path marker represents the aircraft's velocity vector, that is, its actual flight path with respect to the Earth's surface. The flight director provides a steering command to any selected destination. Flight path angle lines show degrees of climb or dive and roll attitude. The heading scale is a conventional magnetic heading display. The airspeed indicator shows 10-knot increments on the vertical scale and 100-knot increments in digital form below. The altitude indicator shows radar or barometric altitude. The pilot selects the next destination. On the head-up display, the pilot turns toward the flight director to bring the aircraft on course. He uses the projected map display to flight follow his position. 2 scales are available to correlate with a forward-looking radar ground mapping display. If the pilot needs to fly low to avoid enemy defenses, the head-up display provides climb and dive commands for terrain following at 5 pilot-selectable altitudes. The radar display also helps the pilot anticipate obstacles ahead in terrain following and terrain avoidance modes. In the Doppler-coupled navigation mode, accuracy is better than 2 nautical miles for each hour flown. 2 inertial modes have essentially the same accuracy. 2 selectable backup modes with lesser degrees of accuracy are also available.
I was less than a mile off course between Hawaii and Wake Island, and this was using pure inertial navigation mode without Doppler.
The pilot can correct navigation errors by performing periodic position updates whenever a landmark with known coordinate location is available visually or on radar, or when any feature on the projected map display can be located visually. Several update techniques are available using the head-up display, the projected map, the radar, TACAN, or by visual flyover. The sophisticated avionics system has greatly reduced pilot workload in navigation or weapons delivery and dramatically increases accuracy. To set up an attack, the pilot selects the appropriate attack mode and establishes the quantity and interval of ordnance to be dropped. Regardless of the attack mode, the pilot's procedure is the same. First, he identifies the target, either visually or on radar. Next, he manually slews the HUD aiming reticle or the radar cursors over the target. This designates the ground location to the computer, which stabilizes the reticle on the target. Now, the pilot follows azimuth steering cues provided by the azimuth steering line. He is free to fly any elevation profile. The computer continuously calculates bomb range, wind, and cross-range corrections. Solution cues appear when in range for the selected weapon. As either cue slides down the azimuth steering line, the pilot can anticipate the point of release which occurs when the cue intersects the flight path marker. The lower cue is used for low angle and toss releases, and the other for high angle releases. The pull-up cue slides up the azimuth steering line, helping the pilot anticipate the point of pull-up to avoid terrain or bomb blast. When range to target equals bomb travel, the computer automatically releases the ordnance, and the flight path marker flashes. After weapon release, and with ordnance remaining on selected stations, the azimuth steering line will indicate re-attack steering back to the designated target. Pilot procedures other than aiming are the same in all computed bombing modes: visual, visual offset, radar, radar offset, and navigation bomb. In the gun and rocket mode, the aiming reticle represents the computed impact point. The pilot simply flies the reticle on the target and fires. For the air-to-air gun mode, the pilot simply tracks the target and fires. Success in combat also depends on survivability. The weapons delivery system and tight turning ability of the A-7 makes it a difficult target. Other survivability features include armor plates of steel, aluminum, or ceramic to protect the pilot from the front, bottom, and sides. Engine protection is arranged on the bottom and sides. Hydraulic actuators are protected by steel plates. Critical fuel cells and lines are self-sealing. Foam baffles in the cells minimize the possibility of fire due to battle damage. A triple redundant hydraulic power control system. The 3 systems are separate except at the dual system tandem control actuators. The A-7 can safely exit the target area, return, and land on any one of these hydraulic systems.
Echo is 50. I was just wondering if you heard anything on those Alpha 7 jets. Roger that. Covey's putting him in on the gun placement at this time.
50, roger that. Okay, we're just about over the intersection of the canal that runs south and the kind of a river that runs parallel with the main river. Okay, look out to the west and I'll put a smoke down.
A flight of A-7s did the most outstanding work in a close troops-in-contact situation I have seen in my 900 hours and 11 months of FAC experience. Their bombing was superb, and I was able to move them right to the perimeter within 25 meters of the friendlies.
And there's smoke on the ground.
Okay, from that smoke, the gun pit is about 10 meters, maybe not even that far directly east, so that's where we want the first one.
Okay, understand.
And I got you all inside.
Everybody got it? Okay, lead's coming around to the south here. Why don't you get ready to put one more in there if you would, Covey?
Roger that, and I'll put one down now.
Okay, green them up. Okay, lead's rolling in.
I've got you in sight. Continue, and you're cleared hot. Good bombs. And Lee, I think you put them right on top of that gun pit.
I hope so.
Okay, 2, let's move it to the east. To about halfway between his and the green spot.
Roger that.
Got you in sight, 2. You're cleared hot.
Roger.
Good bombs, 2. Let's move it to the southwest. Along that little trail, 50 meters.
And for eastern.
Okay, 3. Halfway between the two sets of
To
bombs.
hit what you can see and not be locked in to roll-in altitude, dive angle, airspeed, and release altitude is the primary reason why the A-7 has achieved such outstanding success in combat.
Outstanding. Okay, lead will turn base here, Covey. Okay, do full flight, all switches off, and lights on, out of combat.
Since its inception, the A-7 has constantly been improved. The latest in the family is the two-place A-7. Each cockpit has full flying and communication equipment. Flight characteristics are the same as the single-seat A-7. The U.S. Navy will use it as a trainer with potential as an effective combat aircraft. The A-7, with its advanced avionics, offers potential for increased capabilities in tactical employment. An effective night attack capability has been demonstrated using an infrared sensor in conjunction with existing A-7 avionics. A simple computer software modification allows the employment of a navigation offset bomb technique, highly effective in low-ceiling, restricted visibility conditions. This is only one of a number of improvements that are being made to the A-7.
For my money, you just can't beat the A-7. It's a sophisticated combination of all the factors that make a first-line close-in fighter. You need accuracy and a big ordnance capacity. You also need loiter time, survivability, turnaround speed, maneuverability, and an all-weather attack capability. And the A-7 has it all.